This is a tale about our experiment, where we thought fish and amphibians were the stars. In the Lookout Creek watershed of Oregon's Cascade Range, there are the aquatic vertebrate consumers. Cutthroat trout, coastal giant salamanders, and Paiute sculpins eat invertebrates that live in the creek, insects that fall in the water, and sometimes even smaller vertebrates. Tailed frog tadpoles eat algae growing on the rocks while they live in the stream, until they metamorphose into land-dwelling frogs. Many aquatic invertebrates eat bits of litter and algae. Where does the energy that drives this food web come from? Primary producers, bacteria, algae, mosses, and other aquatic plants need sunlight and nutrients in the water to grow. Primary producers take up nutrients through water flowing in the stream, in the gravels of the stream bed, and welling up from the groundwater. We expect that if there were more sunlight or more nutrients, there would be more bacteria and algae. That would make more food for invertebrates and tailed frogs, and eventually top vertebrate consumers like trout and giant salamanders. But would we see the same results if the numbers of consumers were different? In our experiment, we added nutrients and measured what happened when we added or subtracted out the number of vertebrate consumers. We conducted our experiment over 3 summers, beginning in 2014. Our team created 3 treatments that were between 60 and 75 meters long in the creek. We had a reference reach with the stream's original number of animals, a depletion reach where we took many of the animals out, and an addition reach to which we added more animals. We separated the reaches with nets to prevent animals from moving between study areas during our experiment. We also watched to see what might happen at a smaller scale in small cages that we made out of wooden frames and wire mesh. We placed these cages in each of our study reaches and filled them with baskets of stream cobbles. In the second year of our study, we repeated this experiment in 3 stream sections: Upper McRae, Lower McRae, and Lookout Creeks. By repeating the experiment in 3 places at the same time, we improved the opportunity to see a pattern and reduced the probability that our results were due to chance alone. The top predators in our streams were cutthroat trout, coastal giant salamanders, and Paiute sculpin. We collected them using an electrofisher that sends a weak electrical pulse through the water that stuns them. This captured them safely and made it easier to measure and transfer them for our experiment. At the beginning of the experiment, we weighed and measured these animals to estimate the total animal biomass in each study reach. Our experiment began after the fish and amphibians were placed into the experimental reaches. We added several forms of nutrients, including ammonium salts and propane gas, to track flow paths in the stream. Throughout the experiment, we measured stream flow and took water samples at every reach. During photosynthesis, plants combine energy from sunlight with carbon dioxide to make plant tissues and give off oxygen. More algal growth results in more oxygen. In our experiment, we wanted to know how algae grew in response to consumer numbers and nutrients. So, we took rocks out of the experimental cages, sealed them into plexiglass chambers, and measured the oxygen the algae produced to get a precise measurement of algal growth. We hypothesized that the amount of algae growing would depend on how fast the water was flowing and the number of consumers. Exposing algae to different flow was easy. There were different stream flows in our replicate reaches, and summer flows over the 4 years of sampling were naturally different. The design of the experiment provided natural, lower, and higher numbers of vertebrates. We are only beginning to understand these relationships, even after 3 summers' work. When we removed fish and amphibians, the nutrient ammonium disappeared faster, probably because there was more algae. But our chemical analysis suggests that when we added fish and amphibians, the role of bacteria may have been more important. Scientists at other streams in North America and in Australia have conducted the same experiment, and we have seen some overlapping stories and some different tales from each of these places. Aquatic primary producers and animals are interconnected in complex ways. We are continuing our experiments to test our new ideas about the importance of bacteria and the role of the algae-eating consumers. Stay tuned.